Hello everyone. Here is a problem that sounds almost too obvious to ask. Your system is getting slower, traffic is increasing, so what do? You add more servers, right? One server becomes 10, surely the system should become faster, right? Not necessarily. In fact, you can add more and more servers and still have almost the same performance. So, why does that happen? And more importantly, when does adding servers actually help? Let's take a simple system and find out. Let's make this concrete with a very simple system. We have users sending 10,000 requests every second through a load balancer. Those requests are distributed across three application servers. Now look at the current snapshot. The application servers are using only around 40% CPU. So, from the application tier's perspective, we still have plenty of headroom. But here is the interesting part. The average request latency is 800 milliseconds. And for the users, the experience is simply slow. Now think about that for a moment. The servers aren't overloaded. We have CPU capacity available, and yet the system is still taking 800 milliseconds to respond. So, here is the question. If the application servers have capacity, what's actually slowing the system down? And this is where most engineers would probably make a very reasonable suggestion. Let's just add more servers. So, what's the obvious thing to do? Traffic is high, the system is slow, we have room to add more machines. Let's add more servers. We start with 3, then we scale to 6, 12, and eventually 24 servers. The thinking seems perfectly reasonable. More servers means more capacity, and more capacity should mean more speed, right? But remember what we saw in the previous slide. Our application servers weren't even close to being overloaded. So, before we keep throwing more machines at the problem, there is a more important question we need to answer. Will adding these servers actually make the system faster? Let's find out. Because sometimes you can go from 3 servers to 24 and barely move the needle. So, we did it. We went from 3 application servers to 24. That's 8 times as many servers. And remember, the original servers were only using around 40% CPU. So, we added a huge amount of capacity to the application tier. Now, look at the result. Our latency went from 800 milliseconds to 760 milliseconds. That's an improvement of just 40 milliseconds. 21 additional servers, and we barely moved the needle. Why? Look carefully at the architecture. All those application servers are still talking to the same database. The database hasn't changed. It is still processing the same workload, and it is still the limiting factor. So, we added capacity where we didn't need it. But we didn't increase the capacity of the thing that was actually holding the system back. More servers didn't fix the problem because we didn't fix the bottleneck. So, before I show you the answer, let's stop here and think about this as an architect. We increased the application capacity by 8 times. 3 servers became 24, and yet the system is still slow. So, where is the time actually being spent? What is the application tier waiting for? If you were debugging this system in production, what would you look at next? Would you keep adding application servers? Or would you look beyond the application tier? There is a fundamental idea hiding behind this problem. And once you understand it, you will start looking at scaling problems very differently. Let's uncover the bottleneck. Here is the first principle I want you to remember. A system is limited by its bottleneck, not by its strongest component. Think about the architecture we just saw. We could have 10 application servers, each capable of handling 5,000 requests per second. Together, that gives the application tier a theoretical capacity of around 50,000 requests per second. That sounds like a lot of capacity. But every request eventually has to pass through the data tier. And if our database can sustain only around 1000 relevant operations per second, then that database becomes the limiting factor. It doesn't matter that the application tier can handle 50,000. The system cannot magically process 50,000 requests if the next component can only process 1000 operations. This is why simply adding more application servers didn't solve our problem. We were strengthening the part of the system that already had capacity. We needed to find and address the part that didn't. And that gives us a much better question to ask when a system is slow. Not how many more servers should I add, but what is the bottleneck right now? And in our example, the first bottleneck is pretty obvious. The database. Remember our original system. We had 3 application servers and we scaled that tier aggressively. 5 times the application capacity. But here is the catch. Every single one of those application servers still has to talk to the same database. 10,000 requests per second come in. The load balancer distributes those requests across our application servers. App 1 handles some, App 2 handles some, and so on. From the application's perspective, we have created plenty of parallel capacity. But look at what happens next. All of those requests eventually converge on one database. And suppose that database can sustain only around 5000 relevant operations per second. We can keep adding application servers, but we are still sending more and more work toward the same limited resource. So, the application tier isn't necessarily the problem. The problem is that we have scaled the upstream component while leaving the downstream bottleneck unchanged. That's why adding more application servers doesn't automatically increase the throughput of the entire system. Many app servers and one database. Everything eventually funnels through that same point. And that funnel is the important part of this architecture. Let's make that constraint even more obvious. Look at all of these application servers. We can keep adding more: 5 servers, 10 servers, 50 servers. And at the application layer, our capacity keeps going up. In this example, the application tier can handle roughly 50,000 requests per second. But now look at what happens downstream. Every one of those requests eventually has to pass through the same database, and that database can handle only around 5,000 operations per second. So we have something that looks like this: a very wide top feeding into a very narrow bottom. That's the funnel. We can keep increasing capacity upstream, but if downstream capacity doesn't change, the extra capacity doesn't translate into additional end-to-end throughput. In fact, we may simply be sending more work toward the same constraint. And this gives us a very reusable system design principle. Adding capacity upstream doesn't help if downstream capacity remains unchanged. The system doesn't magically become capable of processing 50,000 requests per second just because the application tier can accept them. The bottleneck still determines what the system can actually process. And that's why, as architects, we shouldn't start with how many more servers should we add. We should start with what is limiting the system right now. Once we find that constraint, then we decide whether to remove it, scale it, partition it, cache around it, or redesign the workflow. Because the goal isn't to make one layer stronger. The goal is to increase the end-to-end capacity of the system. And the database is only the first example. There are many other things that can become that narrow point in the funnel. For example, what happens when the bottleneck isn't the database at all, but a shared resource that every application server depends on? Now, the database isn't always the bottleneck. And this is an important distinction. Because when we say find the bottleneck, we shouldn't immediately assume the answer is the database. The bottleneck could be any shared resource that multiple application servers depend on. For example, imagine we have 5 application servers, all talking to the same Redis cluster. Redis might be able to handle, say, 10,000 operations per second. Now we add more application servers. 5 become 10, 10 become 20, and have we increased the capacity of the system? Not necessarily. We have actually increased the number of servers sending work to the same shared Redis resource. So, instead of creating more useful throughput, we may simply create more pressure on Redis. And there is another very common example. Imagine every application server needs a database connection. But instead of looking at the database itself, let's look at the connection pool. Suppose our available connection capacity is limited to 100 connections. Now we keep adding application servers. Each server wants connections. Eventually, that pool becomes exhausted. And what happens? The requests don't magically become faster. They wait. And when requests wait, latency goes up. So, notice what happened. We added compute capacity. But the shared resource didn't scale with it, and that shared resource become our new bottleneck. And this pattern appears everywhere in distributed systems. It could be a database, Redis or another cache, a connection pool, storage, a file system, an external API, a message broker like Kafka or SQS, or even a shared log or coordination service. The technology changes, but the architectural pattern is the same. Adding servers can increase pressure on a shared resource instead of increasing useful throughput. That's the key idea. And this is why simply looking at CPU utilization on your application servers can be misleading. Your servers might be sitting at 40% CPU, while requests are waiting on something else entirely. So, the goal isn't how do I add more servers? The goal is what resource is actually limiting throughput and how do I remove or scale it? And sometimes, even after we have identified a shared resource, there is another kind of bottleneck that's even more subtle. The system may not be waiting for a resource at all. It may be waiting for other machines to coordinate with each other. That's where things get really interesting. Let's look at coordination as a bottleneck. So far, we have seen two kinds of bottlenecks, a database and a shared resource like Redis or a connection pool. But there is another category that's a little more subtle. Sometimes the bottleneck isn't a resource at all, it's coordination. Imagine we have 5 application servers. Each server can process requests independently. At first, that sounds great. But what if these servers need to agree on something before they can proceed? Maybe they need to acquire a distributed lock. Maybe one server needs to become the leader. Maybe they need to maintain some shared state. Maybe a transaction needs coordination. Or perhaps multiple servers need to synchronize before performing an operation. Now, suddenly, our independent servers aren't really independent anymore. They have to communicate, they have to wait, they have to agree, and that communication introduces coordination overhead. And here is the interesting part. When you add more machines, you might expect the system to simply become more powerful. But if those machines have to coordinate with each other, adding more machines can actually create more coordination work, more participants, more messages, more state to keep consistent, more opportunities to wait. So, the relationship isn't always more servers to more throughput. Sometimes it's more servers to more coordination to more overhead. And at sufficient scale, that coordination itself can become the bottleneck. Think about distributed locks, leader election, shared state, cache and validation, transactions, synchronization. These mechanisms exist for very good reasons. We need them to preserve correctness, but correctness comes with a cost. And as architects, we need to understand that cost. This is one of those places where a system can look perfectly healthy from a CPU perspective. The servers aren't necessarily overloaded. The database might even have plenty of capacity. But requests are spending time waiting for coordination. And that's why coordination is such an important consideration in distributed systems. It doesn't always show up as one obvious server that's running at 100%. Instead, the overhead is distributed across the system. The key takeaway is coordination doesn't scale linearly. As the system grows, the coordination required to keep everything synchronized can grow too. And eventually, coordination itself becomes the bottleneck. So, now we have seen three very different bottlenecks: a database, a shared resource, and coordination. But there is still one more bottleneck that architects encounter all the time. And this one is especially important in distributed systems because it might be completely outside our system. What happens when our service is fast, but the service we are calling isn't? Now, let's take this one step further. What if the bottleneck isn't inside our system at all? Imagine our service has 20 application servers. Those servers are perfectly capable of handling around 50,000 requests per second. So, from our perspective, we have plenty of capacity. But our service needs to call a payment provider, and that payment provider can handle only around 2000 requests per second. Now we have a problem. We can add another 20 servers, we can add 100 servers, we can make our own application faster, but none of that changes the capacity of the payment provider. The requests still have to go through it, and if the payment provider is the limiting factor, that's where requests will start waiting, timing out, or getting rejected. This is why I like this simple rule. Your system is only as fast as its slowest dependency. And notice something important here. The dependency doesn't even have to be a service you own. It could be a payment gateway, an SMS or email provider, a shipping API, a third party API, an external SaaS platform, or any other service that sits in your request path. This changes the way we think about scalability. When you are designing a system, don't just ask, can my service handle the traffic? Ask, can the entire end to end flow handle the traffic? Because your service might support 50,000 requests per second, while the dependency immediately downstream supports only 2000. Your effective throughput is constrained by that dependency. And this is where architecture becomes more interesting. Because you can't simply walk into a third party payment provider and say, hey, we are scaling today, please add 20 more servers. You don't control their infrastructure. So, you need architectural strategies to deal with that constraint. Maybe you introduce asynchronous processing. Maybe you use queues. Maybe you batch requests. Maybe you cache where it's safe to do. Maybe you implement backpressure, rate limiting, retries with care, or graceful degradation. The right strategy depends on the dependency and the business requirement. But the first step is always the same. Focus on the end to end flow. Don't stop measuring at your service boundary. Trace the request all the way through its dependencies. Because sometimes the bottleneck you are looking for isn't in your architecture diagram's biggest box. It's somewhere outside your system boundary. And now we have an interesting question. What happens when we have identified a bottleneck, but the bottleneck can't process work as quickly as we are sending it? That's where queues enter the picture. Let's look at the queuing problem. So far, we have established something important. Adding more application servers does not automatically make the system faster. But there is another effect we need to understand. Queues. When we add more servers, we increase the amount of work the application tier can accept and process concurrently. That sounds great. But what happens when all those servers are sending work to a bottleneck that cannot process requests at the same rate? That's where the queue appears. Let's start with the healthy case. If the incoming request rate is less than or equal to the server's processing capacity, requests arrive, they get processed, and they leave. There is no significant waiting. Low queue, low latency. Now look at the other side. Here we have multiple application servers. They can process a lot of requests concurrently, but all of them eventually send their work to the same shared bottleneck. And that bottleneck has a fixed capacity. If requests arrive faster than the bottleneck can process them, what happens? They don't disappear. They wait. That waiting area is the queue. And this is one of the most important ideas in performance engineering. When demand exceeds the capacity of a component, the excess work becomes waiting time. And notice something subtle here. The application servers may still look perfectly healthy. CPU might not be maxed out. Memory might be fine. We might even have plenty of servers. But users can still experience increasing latency because their requests are spending more and more time waiting for the bottleneck. As utilization of the bottleneck approaches its maximum capacity, the queue can grow rapidly. And once the queue grows, latency follows. So, you can end up in a situation where the system isn't technically overloaded everywhere, but users still feel that the system is slow. This is why simply adding more servers can sometimes make the situation worse. More servers can create more concurrency. More concurrency can push more work toward the same bottleneck, and that can mean a bigger queue, not necessarily more useful throughput. The queue is absorbing the excess demand. So, when you see latency increasing, don't just ask, do I need more servers? Ask a better question. Where is the work waiting? Because that waiting point often tells you where your real bottleneck is. And once you identify that bottleneck, the next question becomes, what does this actually look like in a real production system? Let's look at a real example. Imagine we are building an e-commerce checkout system. We start with 10 checkout servers. Users come in through the load balancer, and the checkout request flows through several downstream dependencies. The inventory database, then the payment service, and finally the order database. At this point, our checkout latency is around 2 seconds. The team looks at the application servers and thinks maybe we are running out of checkout capacity. So we do the obvious thing. We add 10 more servers. Now we have 20 checkout servers, more capacity, more concurrency. It sounds like checkout should become faster. But here is what actually happens. The latency is still around 2 seconds. So, what went wrong? Did the new servers not work? No. The new servers are perfectly capable of handling more requests. The problem is that every request still has to go through the same downstream path. And one of those dependencies, the inventory database, has limited capacity. That database can process only so much work at a time. So, when 20 checkout servers send requests toward it, we are not magically increasing the database's capacity. We are simply sending more concurrent work toward the same bottleneck. And what happens to that extra work? It waits. That's the queuing problem we just discussed. The checkout servers can scale horizontally, but the inventory database hasn't scaled with them. So, the end to end request is still constrained by that bottleneck. That's the queuing problem we just discussed. The checkout servers can scale horizontally, but the inventory database hasn't scaled with them. So, the end to end request is still constrained by that bottleneck. And notice something else. The payment service and order database might have plenty of capacity. That doesn't matter. A request has to complete the entire journey. If one critical dependency is slow, the overall request can still be slow. This is why architects have to think about the end to end flow, not just one layer in isolation. The lesson here is simple. Adding more servers at the application tier doesn't help if the downstream dependency can't keep up. So, instead of asking, how many servers should we add? Ask, where is the request spending its time? Measure the flow, identify the bottleneck, and then optimize that. Because once you understand where the constraint actually is, you can make a much better scaling decision. And that brings us to an important question. When does adding more servers actually work? Let's look at that next. So, we have spent quite a bit of time talking about why adding servers doesn't always help. But I don't want you to walk away thinking horizontal scaling is a bad strategy. It's one of the most powerful scaling techniques we have. The real question is, when does it actually work? The answer is when the workload is parallelizable. In other words, when we can take the incoming work, divide it across multiple machines, and have those machines process their work independently. Imagine we have 4 application servers behind a load balancer. A request comes in. The load balancer can send it to server 1. Another request goes to server 2, another to server 3, and another to server 4. Each server can process its assigned requests independently. There isn't a single shared resource forcing all of those requests through the same narrow path. That's the key. This kind of workload typically has a few important characteristics. It's stateless, it's independent, it's often CPU bound, and most importantly, each server can process requests without needing to coordinate with every other server. Now, look at what happens to throughput. If one server can handle roughly 10,000 requests per second, then two servers can handle roughly 20,000 requests, and four servers can handle roughly 40,000. The numbers wouldn't always scale perfectly in the real world because there is overhead. But the important idea is that throughput can increase almost linearly as we add servers. Here, adding servers is adding useful capacity. That's very different from our earlier checkout example. There, we added servers, but all those servers were eventually waiting on the same bottleneck. Here, the work is actually being divided. Each server contributes additional processing capacity. And this gives us a very useful rule of thumb. Horizontal scaling works when three things are true. The workload can be parallelizable. There is no single shared bottleneck limiting everyone. And the machines can process their work independently. So, here is the architectural distinction I want you to remember. Horizontal scaling is not about adding machines, it's about adding independent capacity. You can have 100 servers and still have the same system capacity if they are all waiting on one shared bottleneck. But if each additional server can do useful work independently, then adding servers genuinely increases throughput. And now we know when adding servers works. The next question is, what do we do when the bottleneck itself is the problem? That's where we need to scale the bottleneck. We have now seen several different kinds of bottlenecks. It could be the database, it could be a shared cache, it could be a connection pool, it could even be an external dependency that we don't control. So the question becomes, what do we actually do when we find the bottleneck? And this is where I want to introduce a simple process that you can use in almost any system. Don't start with how many more servers do we need? Start with a much better question. What is limiting our throughput right now? Because adding capacity without understanding the bottleneck is often just adding cost. Step 1, measure. Before changing anything, collect real data. Look at throughput, latency, CPU utilization, memory, connection pool uses, queue depth, cache evictions, database load, and importantly, look at the end-to-end request flow. Because the bottleneck isn't always where you expect it to be. A dashboard might tell you that your application servers are sitting at only 40% CPU. That doesn't mean the system has 60% more useful capacity. Something downstream might already be saturated. Step 2, find the bottleneck. Identify the component that is actually limiting throughput. For example, maybe your application tier can process 50,000 requests per second, but your database can process only 5,000. Then, adding more application servers doesn't solve the problem. The database is still setting the ceiling. But finding the bottleneck isn't enough. We also need to understand why it is the bottleneck. Is it simply a capacity problem? Is the CPU saturated? Is there lock contention? Are requests waiting on I/O? Is a connection pool exhausted? Is there coordination overhead? Or is the system waiting on an external dependency? Because the solution depends on the cause. You don't solve lock contention the same way you solve CPU saturation. And you don't solve an external API limitation by adding more application servers. Once you understand the cause, we can choose the right intervention. Maybe add capacity. Maybe we optimize the workload. Maybe we redesign the component. Maybe we remove unnecessary coordination. Or maybe we decouple the dependency altogether. The important point is we scale the constraint, not the component that happens to be easiest to scale. And finally, measure again. This step is incredibly important because an architectural change isn't successful just because the diagram looks better. We need to prove that throughput improved, latency improved, and the bottleneck actually moved or disappeared. And here is the interesting part. When you remove one bottleneck, another bottleneck usually becomes visible. That's normal. In fact, that's how you progressively scale a system. You find the current constraint, improve it, measure again, and then find the next constraint. And these examples are worth remembering. A database running at 90% CPU, Redis experiencing high evictions, a saturated connection pool, a slow external API, a distributed lock experiencing high contention, or a message broker where the backlog keeps growing. These all represent different bottlenecks, and each requires a different solution. So, instead of asking, how many servers do we need? Train yourself to ask, what is limiting throughput right now? That is a much more architectural question because throughput is only as high as your bottleneck allows. And this gives us a very useful mental model. Measure, find bottleneck, understand why, remove or scale it, measure again. And here is the architect's takeaway. Grid systems are not necessarily built by adding more. They are often built by removing what's in the way. And now that we understand how to approach a bottleneck, let's build a practical scaling ladder. Because once we have identified the constraint, the next question is, what should we try first and when should we move to a more expensive solution? So, we have now seen several different kinds of bottlenecks. Sometimes it's the database, sometimes it's a shared cache or a connection pool, sometimes it's coordination between machines, sometimes the bottleneck is actually outside our system, a third party service, or an external dependency. And sometimes the problem isn't capacity at all. It's the way the workload is structured. So the question becomes, how do we approach scaling systematically? Not by immediately adding more servers, but by following a process. Think of this as a scaling ladder. Step 1, observe. First, observe the system in the real world. What are users actually doing? Where does the system become slow? What symptoms are we seeing? Is it latency, errors, timeouts, high CPU, memory pressure, or requests simply piling up somewhere? Because before we scale anything, we need to understand what is actually happening. Next, we measure. And this is where matrices become extremely important. We look at things like latency, P90, P95, P99. For throughput, we looks at requests per second and resource signals like CPU, memory, I/O, saturation, and errors. Because intuition can tell us that something feels slow, but measurements can tell us why. Then we diagnose. This is where we ask the most important question: which component is actually limiting throughput? Is the database saturated? Is Redis evicting aggressively? Is the connection pool exhausted? Is there a distributed lock creating contention? Is an external API responding slowly? And this distinction is critical. We don't want to optimize the component that is merely visible. We want to identify the component that is actually limiting the system. That's the bottleneck. Once we have identified the bottleneck, we optimize it. And optimization doesn't always mean adding capacity. Maybe we can make the operation more efficient. Maybe we can redesign the access pattern. Maybe we can reduce contention. Maybe we can remove an unnecessary dependency. Or maybe we can decouple the workload. The goal is simple: remove or improve the constraint that's limiting throughput. Only now do we scale. Once we understand the bottleneck and have improved it, we can add servers, scale out, increase limits, distribute the workload. And now adding capacity actually has a chance of improving the system because we are scaling the right part of the architecture. But we are not done. We measure again. Did throughput actually improve? Did latency come down? Did the bottleneck disappear? Or did the bottleneck simply move somewhere else? Because that's something that happens constantly in real systems. You remove one constraint, and suddenly another component becomes the new limit. And that's why I want you to remember this process: observe, measure, diagnose, optimize, scale, and measure again. This is very different from saying we are getting more traffic, let's add more servers. That's not scaling, that's guessing. Good architecture is not about adding capacity everywhere. It's about finding the right constraint and removing it. And that brings us to the most important idea from this entire discussion. Scale is the result of removing the right constraints, not simply adding more machines. So remember three things: measure before you scale, every system has a bottleneck, and most importantly, architects fix the limit, not the symptoms. In the next section, we will take this idea one step further and start looking at how we actually scale the components that become bottlenecks. So, if there is one idea I want you to remember from this entire discussion, it is this: don't scale the servers, scale the bottleneck. Because adding more machines does not automatically create more capacity. If 10 application servers are already sending more work than the database can handle, Adding another 10 application servers doesn't magically make the database faster. It simply sends more pressure towards the same constraint. Think about everything we have seen. The database can be the bottleneck. A shared Redis cluster can be the bottleneck. A connection pool can be the bottleneck. A distributed lock can be the bottleneck. An external API can be the bottleneck. And sometimes the bottleneck isn't even a physical resource. It can be coordination. The important question is therefore not how many servers do we need. The better architectural question is what is limiting our throughput right now? And once we know that, we follow a very simple loop. Observe what is actually happening, find the limit, remove it, improve it, or scale it, and then measure again. Because after you remove one bottleneck, another one may become visible. That's normal. In fact, that's often what scaling a real system looks like. You don't eliminate bottlenecks forever, you move the bottleneck forward. And each time you do that, the system can handle more useful work. So remember this line. The bottleneck determines the system's effective capacity, not the number of servers, not the amount of infrastructure we have deployed, not how impressive the architecture diagram looks, but the bottleneck. And that is one of the biggest differences between simply adding infrastructure and actually engineering for scale. At the bottom of the slide is the mindset I want you to carry with you. Don't guess, measure, then act. Because good architects don't ask, what can we add? They first ask, what's actually getting in the way? And that brings us to the end of this discussion on bottlenecks and scaling. Let me leave you with one question. In system design, the interesting question isn't how many servers do I have? It's what prevents me from adding more throughput. Because more servers don't necessarily mean more capacity. If the database is the bottleneck, if a connection pool is exhausted, if a shared cache is saturated, or if an external dependency is limiting us, adding more application servers simply pushes more work toward the same constraint. And this is the mindset I want you to take away. Observe what is really happening, measure the system, find the bottleneck, remove or improve the constraint, and then measure again. Because once you remove one bottleneck, the next one may appear. And that's okay. That's how scalable systems evolve. As we continue through this system design series, we will keep coming back to this same way of thinking. We will take one architectural concept at a time. We will go deep into how it works. We will look at where it helps in real world systems. We will explore the trade offs. And most importantly, we will develop the architect's mindset behind the technology. Because ultimately, system design isn't about memorizing components, it's about asking better questions. And better questions lead to better systems. If you enjoyed breaking down system design problems this way, consider subscribing to the channel. I will be exploring one architectural concept at a time with practical examples and the trade offs that matter when you are designing real systems. And if you found this useful, Turn on notifications so you don't miss the next one. Thanks for watching, and I will see you in the next system design deep dive.